Hello again. Today we're going to be looking at the distance between parallel lines. So first things first, definition. The distance between two parallel lines is the perpendicular distance between one of the lines and any point on the other line. We're going to see an example of this here shortly. We also have a theorem that if in a plane two lines are equidistant from a third line, then those two lines must be parallel to each other. To understand this, we really need to understand what equidistant or equidistant means. So the definition here kind of goes with parallel lines. The distance between two lines that's measured along a perpendicular is always the same. That's what we mean by equidistant lines. The distance between them remains constant. Now, lines are parallel if they are equidistant, and you could really phrase this as an if and only if, or a biconditional. Lines are equidistant if they are parallel. Okay, so we're going to look at an example of finding the distance between two parallel lines. Here, those lines are A and B, and we start out with their equations. Notice, of course, we have the same slope because they are parallel lines, different y-intercepts. So the goal is to figure out this perpendicular distance. Now I've drawn it on the graph in a couple of specific places, but really it could be anywhere. Let's add, it could be down here, or even further down here, up here. All of these, as long as those are perpendicular segments between those parallel lines, represent the same distance. Now, I've called out like these two in particular because they kind of simplify the process a little bit. So let's talk about why and how we choose those spots. These segments, of course, are along perpendicular lines, so they're going to have opposite reciprocal slopes to the original parallel lines. And like I said, there's all these different options we could choose from. So why do I have two called out in particular? Well, in general, we're going to need to know the coordinates of these two different points on A and on B, on A and on B. And if I reuse one of these spots, reuse a y-intercept, then that basically cuts the amount of work I have to do in half because I don't have to figure out that intersection point. I don't have to figure out the coordinates of that point. I already have it. It just is the y-intercept and is given from my original equation. So we could pick either of these. It's kind of up to us. You could really make it harder for yourself and not use the y-intercept, but I don't know why you would ever actually want to do that. So I'm going to go ahead and run with, let's say, the y-intercept of A. I'm going to say that I'm going to make some perpendicular line that goes through that y-intercept or shares that y-intercept. So we need to write the full equation of this line, and I can kind of sketch this line here through our y-intercept. Okay, we know it's perpendicular and we know it goes through that y-intercept. So I actually don't have to do very much work here. If the slope of my parallel lines is 2, then the new slope of my perpendicular line, remember, is the opposite reciprocal of those. So negative 1/2, or negative 1/2 is my slope here. Now, I also don't really have to do any work to figure out the y-intercept, our b value here, because we're literally picking it. We're picking it so that it goes through line A right at the y-intercept. They share the y-intercept. So 3 is what I'm going to be using for my y-intercept. So that makes my equation y equals negative 1/2 x plus 3. And just to call this out, you could, as easily as we did this here, we could have actually used the p that I have drawn here and reused the y-intercept of negative 1. neither is like harder or easier than the other. Just means what we do next is a little bit different. Like I'm going to go ahead and solve for now this intersection point between my purple line that I'm going to call P and B. Whereas if you use the y-intercept -1, then you'll need to figure out this other intersection point of P and line A. Either way, we still are going to go through the process in a very similar fashion. Okay, so the equation I am using for P, I realize this is a little confusing because I went with the other line. Let me sketch it here. The equation that we just wrote for line P is y equals -1/2 x plus 3. And I need to know this intersection point between line P and line B. And from the graph, we can tell it's not exactly going to be like a nice point. It's going to have maybe some decimal or fraction coordinates to it. It's not at the intersection of grid lines like we like. Now we're looking for that point because we already know this one. We already know where line A and P touch, and that's right at the intercept, y-intercept of 0, 3. So if I can figure out the x and y coordinates of the other intersection, then I'll be able to find the distance between them. Okay, so let's take that equation for P, y equals -1/2 x plus 3. Now I'm going to also look at line B, so y equals 2x minus 1, and I want to know where do these two cross. System of equations is going to help me solve for those two coordinates, x and y coordinates. Now I'm going to use elimination for this. So I'm going to basically set these two things that are equal to y equal to each other. So 2x minus 1 equals -1/2 x plus 3. Okay. Now we can just solve for x, like, add 1/2 x to both sides and that kind of thing. But to be honest, I like when I have fractions like this, I like to try to get rid of them if I can. And by get rid of, I mean, like, how would I actually have this be a whole number, this -1/2? If I were to multiply it by 2, it would all of a sudden just be a -1x. So I am going to take this entire equation and multiply it by 2. So really that's using my multiplication property of equality. We're multiplying both sides by 2. And that means everything on both sides. The 2 times 2x gets us 4x. 2 times -1 means -2. Now 2 times -1/2 x means we'll have -1x or -x. And 2 times 3 means I'll have 6. And this just means I have whole numbers to work with, at least for now. A little bit nicer. So maybe I'll add x to both sides to get 5x and add 2 to both sides to get 8. And we still have to divide by 5, and here we can see, oh, we're still going to have fractions after all. So 8/5, or you could say that's 1 3/5. I'm going to leave it in this improper fraction form for now. So that's my x coordinate. We can kind of confirm using the graph that, yeah, that does look about 1 3/5, 1 point, whatever. So now we need to figure out the y coordinate, and we're going to plug our x coordinate back into either of our equations, either y equals -1/2 x plus 3, or y equals 2x minus 1, either one. I'm going to go with the equation for B. So y equals 2x, but actually 2 times 8/5 minus 1. So let's simplify this, and looks like this is also going to be a fraction, right? 2 times 8/5 is like 16/5. And I'm going to rewrite 1 as 5/5 so that I can actually subtract these pretty easily. 16/5 minus 5/5 would give us 11/5. So our coordinates of the intersection between line B and my line P is going to be 8/5, comma 11/5. Okay. So the last step is going to be to figure out the distance between those two intersection points. Yes, one of them is that fraction, the fraction coordinates, and one of the points is 0, 3. So we have our work cut out for us. Okay, I'm going to, again, maybe rewrite those points here. What was it? 8 over 5, 11 over 5, and 0, 3. Okay. So we showed in the previous example using just the Pythagorean theorem, but we can also use our distance formula strictly. So remember that distance formula looks like this. D for distance equals the square root of, and then we can say x1 minus x2 squared plus y1 minus y2 squared. That is our distance formula. So if you prefer working with it like this, great. If you prefer the Pythagorean theorem, also great. Either works for me. So I'll go ahead and maybe stick with the formula since that's what I have going. Okay, now we have fractions. All right, so let's take our x-coordinate of 8 fifths first. Now we're only subtracting 0, so that's kind of nice, but we are going to have to square that. All right, and we have next our y's. So 11 fifths minus, now 3 is the other y coordinate, but I'm going to go ahead and write that as 15 fifths so that I can actually subtract those numbers. We're squaring that difference and taking the square root of all that. Okay, so that comes out to 8 fifths squared plus, all right, so 11 minus 15 is negative 4 fifths, all squared. Okay. Now when we square fractions, remember we square the numerator and the denominator, so what we really have is 64 25ths now plus 16 25ths. Okay, so we can add these fractions. Remember, the square root serves as like a grouping symbol, so we have to simplify everything underneath it before we can actually take the square root of these numbers. I know it's unfortunate because those are all nice square numbers. Seems like we could just take the square root of all of them right now and keep life a little simpler, but unfortunately that's not what our order of operations tells us. Instead, we have to add 64 and 16 to get 80 25ths. And now we have this fraction that we have to take the square root of. And we take the square root of the top and the bottom. So I'm going to draw an arrow going this way with it to save space. We have the square root of 80 over the square root of 25. So that denominator simplifies nicely to just 5. And our numerator, we can break that apart. Square root of 80 can be broken into the square root of 16 times the square root of 5. So this will simplify to 4 times the square root of 5 over 5. And that represents ultimately the distance between our parallel lines A and B.